Number 11. A model rocket flies horizontally off the edge of a cliff at a velocity of 15 meters per second. If the canyon below is 100 meters deep, how far from the edge of the cliff does the model rocket land? And they gave you acceleration due to gravity. So those are your choices. Do a sketch and see if you can figure this out. Find the right formula in your formula sheet or page 58. Alright, so let's do the given first. You know the velocity in the x direction because you threw it horizontally off the cliff. So it's going horizontally at 15 meters per second. Now, you threw it horizontally, so you must know that the initial velocity going down is 0 meters per second. That'll help you figure out what formula to choose later on. Now, the displacement is how far it falls down off the cliff in the y direction. So that's a negative 100 meters. Then you know the acceleration due to gravity, which is negative 9.81 meters per second. They want you to find the displacement in the x direction. How far from the cliff does it land? So, now you have to say, what formula do I need? Is there something else I need? So I want you to think about that right now. Alright. Now, believe it or not, you need something. The vertical component of this problem will get you time. Alright, because you're starting at 0 meters per second, its initial velocity in the downward direction is going to be 0. So the formula you should use is a formula we've used a lot for displacement, which is the change in y is half times the acceleration times squared. Then if you want to find time, you've got to rearrange everything algebraically, and it leads to time equals the square root of 2 times displacement over acceleration. Now the reason you want time is because you want to find out how far it went horizontally, which is the displacement in the x direction. So here's the formula you're going to use for that, which is average velocity equals displacement over time. You get rid of the time because you want displacement in the x direction, so you're going to multiply time by both sides. Cancels out here, so this is now the formula you're going to use. You get your final answer. Displacement is the change in time times average velocity. So let's solve for time first. Let's go use this formula up here. So plug it in. Plug it in as I show it to you. Just make sure I didn't make a mistake. The square root of 2 times negative 100 meters divided by a negative 9.81 meters per second squared. Did I come up with the right answer? Double check me. Alright, so it's 4.52 seconds. Now I'm not too worried about sig figs right now because I'm not done with what I'm looking for, which is this formula. So let's go to the next slide. So displacement, remember, is the average velocity times the change in time. Now the velocity coming off the cliff was 15 meters per second horizontal, so it's going sideways, but it didn't say anything about acceleration, deceleration sideways. So if it doesn't say it, just as, I want you to make the assumption here that it's going 15 meters per second all the way sideways until it hits the ground. So all the way sideways is going 15 meters per second until it hits the ground. So what determines when it hits the ground? The time right here. And we figured it out earlier with that displacement equals half times acceleration times squared from the previous slide. So here's the diagram. This is the projectile motion. It's going to land there. If we measure from there in a straight line to the edge of the cliff, it's going to be 226 meters, so that is the correct answer. I hope you got that. Alright, let's go to the next one. Okay, I know you're getting tired, so stay with it. If you need to take a break, take a break. Come back in 15 minutes. Number 12. Experience a constant horizontal 1.15 meters per second wind. A hot air balloon ascends. So you need to know what ascends means. It means it goes up from launch site at a constant vertical speed of 2.5 meters per second. At a height of 205 meters, The balloonist maintains a constant altitude for 10 seconds before releasing a small sandbag. How far from the launch site does the sandbag land? So, right now, since it said he's maintaining this altitude, so he's 205 meters above the ground, and he's maintaining that, so there's no change there. So you don't have to worry about it going up or down. And then he's going to release the sandbag when it's at 205 meters. And so you want to know how far it's going to land from the launch site. So right now, do a sketch and see if you could figure out this answer. Alright, we're starting with the given. So we know the velocity in the x direction. That was the wind blowing the balloon at 1.10 meters per second. We know the displacement because it's going to fall from 205 meters and it's going down, so it's going to be negative. We know the acceleration due to gravity is negative 9.81 meters per second squared. And what they want you to do is find out the displacement in x direction from the launch site on the ground where the balloon took off to where it landed. So what formula are you going to use? So see if you can find a formula that has displacement, okay, that has velocity, displacement in the y direction, and acceleration. So think about this. Is there something else we need? What else do we need that would help us? Alright. So, once again, we come back to this velocity formula, which is displacement over time. We get rid of the time on this side, so now displacement is the change in time times the average velocity. We didn't say there was a wind blowing beyond the 1.1 meters per second. Now, if you look at this, here is the change in y equals half times acceleration times squared. Why do I use that again? Guess what? To know how far it goes horizontally, you need to know the time, because right here you need time. So you always can find time using the vertical component because you know acceleration. And you know how high that balloon was before it dropped it. So rearrange it, isolate the t, so once again it's the square root of t times displacement over acceleration. Plug in the information that was given. So it's 2 times the negative 205 meters divided by negative 9.81 meters per second squared. You take the square root of that, gives you time at 6.46 seconds. So once you have time, then you could go back to this original formula. Displacement is the average velocity times the change in time. So plug it in. 1.1 meters per second is the horizontal velocity when the bag was dropped, times the time you just calculated from the vertical component. You could use it now for the horizontal, which is the change in x. So the average velocity times the time will give you this answer, 7.106 meters. And then guess again. You got to go back to the beginning and say, how many sig figs do I need? So if you go back to the beginning, if you have to rewind, 3 sig figs. Should be 1, 2, 3, so it's 7.11 meters. That's how far that bag landed from the launch site. Let's go to the next one. Number 13. A small airplane flies at a velocity of 145 kilometers per hour towards the south, as observed by a person on the ground. So that's the person was the reference point. The airplane pilot measures the air velocity of his plane at 172 kilometers per hour south. What is the velocity of the wind that affects the plane? So the person saw it as 145 kilometers per hour, so there has to be some wind affecting it. So you got to do this as vectors, add the vectors together. So do that right now, sketch it and see if you can come up with the right answer. He wants to know the velocity of the wind. Alright, here's a sketch. I know it looks like a bunch of stuff here, so let's just go through this. So here's the original vector going all the way down. That's vector number 1. That's the plane pilot recording 172 kilometers per hour going south. Then the gentleman on the ground saw the plane going south 145 kilometers per hour, which would be right there. So you need to find the difference from here to here, and that must be the wind blowing in the opposite direction. So that wind is blue, so that means that the wind, if you take 172 kilometers per hour and subtract 145, you get 27 kilometers per hour. That has to be the wind. So let's do this mathematically. So the sum of the vectors have to equal a negative 145 kilometers per hour. Why did I put that negative sign there? You know this. That's right, because it's going south. Alright, so let's write down the vectors that we know. We know the pilot recorded negative 172 kilometers per hour. So the negative, because the pilot's going south. Then you say you have to add it to another vector that will give you the negative 145 kilometers per hour. So I want to know what this vector is right here. I could have made this into some letter to represent this, so I just left it as a question mark. So let's move this over. This is addition, so you want to get rid of this negative. Alright, so you got to add a positive to it to cancel it out. So what you do to one side, you got to do the other side, and then do the math. A negative 145 plus 172 gets you 27 kilometers per hour, and that's positive because it's going north. So the wind is blowing north at 27 kilometers per hour. Alright, here is number 14. I didn't have room at the bottom to write this out, but it said that C, the hypotenuse, is equal to a squared plus b squared and the square root of that. So you're going to add the vector a and you're going to add the vector b, and then you'll show me the hypotenuse. Here are your 4 choices. So you could do this 2 ways. You could start with drawing the a or drawing the b. So let's start with drawing the b. If we're going to draw the b first, we go down. Whoops, sorry about that. Let's go back. Jeez. Alright, here's number 14. This one you have to add 2 vectors to come up with the hypotenuse. So it gives you the 2 vectors, A, which is going east, and B, which is going south. So you could start with A and then add B to it, or you could start with B and add A to it. So let's start with A, and then we're going to add B to it. So A would go to the right and B would go down. Oh, wait a minute, this is just like that. That's not adding vectors. When you add vectors, it's head to tail. So number 1's not going to work. Alright, let's look at this one. Alright, so here's the hypotenuse. If this is A, is B going up? No, B is going down, so number 4 is wrong. Let's look at number 3. Alright, what's going on here? We got something going to the west, but nothing's going to the west here. So eliminate that right away. Alright, let's look at this one. This has to be the answer. So, A is going to the right. Here we go. A is going to the right. Then we add the next one to the head of it, and it's going down, and look, it's going down. So that must be B. And then C is from where we started to where we ended. Whoa! It's number 2. That wasn't that hard. Alright, let's go to the next one. Number 15, it's to find the resultant by graphing it with a protractor and graph paper and a ruler. A cave explorer travels 6 meters eastward, then 2.5 meters northward, and finally 15 meters westward. Use the graphical method to find the magnitude of the net displacement. See if you could sketch that out, or if you have a protractor, see if you could come up with the resultant based on making a scale. The scale was 1 centimeter is equal to 1 meter. Give it a shot. Alright, hopefully your graph looks something like this, but a lot smaller. In order for this to show up quite well on this tape, I had to use a little bit different scale just so you can see it. So the first vector was this one. It's 6 centimeters going to the east. Of course that's not 6 centimeters, it's quite long, it's longer than that. Then we used 2.5 centimeters going to the north. Then 15 centimeters going to the west. So the resultant, you don't have to do any math. You just measure from where you began with the first one to where you ended on the second one. That length is the resultant, and it should measure approximately 12.2 centimeters. Then you have to go back to the scale you used on the test, and it was 1 centimeter to a meter, so if it's 12.2 centimeters, it's 12.2 meters. So all you had to do is draw it to scale, and then when you're done, measure how long it is from where you began to where you ended. That length will give you the magnitude. I didn't ask you for direction on this one. So this one, did you really need the protractor? Not really, because look at, we're going east, we're going north, and we're going west. The protractor would have helped a little if you didn't have graph paper and you didn't come right on a line. So this is how you graph it. It's easier than doing it mathematically, but it's less accurate. Well, this is the end of the review for the Chapter 3 Vectors Test, Retest. I hope this benefited you. I hope you watched the video and tried to find the answers before I went over them. If you did not, it's not going to help you much. So, you now are qualified to come in for a tutorial with me and make corrections on your own of the ones we just did. I want you to be honorable and don't copy all these answers down. Come in and do it on your own. You could have taken notes during this film. That's fine. So come in, and then you have to prove to me that you understand this, so I might call you to the whiteboard. So I'll see you soon. Let's get that grade up. Alright, have a good one. Later.